Today we're going to talk about torque and angular acceleration. We talked about torque earlier and understood that we could calculate torque and cause something to rotate if we consider both a radius from the axis of rotation and the force, and how those two things were important to be perpendicular to each other. So the magnitude of torque is proportional to the force and the moment arm. Remember, a moment arm is like leverage, that lever arm. And the torque is at right angles to the plane established by the force and the moment arm vectors. So this is where we learned to use our right hand rule, where we had our index finger for the radius, our middle finger for the force, and then we stuck our thumb out to represent the torque. So torque was R cross F, and it was measured in Newton meters. Let's take a look at a practice problem here. It says, here we have a pulley. We have two masses hanging from this pulley, a 10 kilogram mass, a 2 kilogram mass, and we have a string across the top of it that we're going to apply a force to. In this diagram, they tell us that this has two different radii. Let's take a look and see if we can see this a little better. The axis of rotation of the wheels are at different radii. So the inner wheel is at 2 centimeters and the outer wheel is at 3 centimeters. So we'll have to see which string is attached to which one. So they say, what must F be in order to achieve equilibrium? Clearly, if you let this go, the 10 kilogram block is going to pull down and the 2 kilogram block will be accelerated up and it would rotate in a positive counterclockwise direction. But if we assume there's no friction on the axle and we include this extra force, how much force does that need? Remember, equilibrium means no net force, no net torque. So we want the net torque on the system to be 0. We have 3 different things that are going to provide torque. So we have the torque from the 10 kilogram, the torque from the 2 kilogram, and the torque from our pull, or the force. And we want to add these up and make them equal 0. So remember, torque is radius times force, and we want these to be perpendicular to each other, so we have to include the sine of the angle between R and F. If it's 90 degrees, then sine of 90 is 1, and so we're all good. But this helps us to get that perpendicular component using sine theta. So the radius of the pulley times the force of the 10 kilogram mass times the sine of the angle between those two. Well, this force and this radius are going to be at 90 degrees, so we'll be okay there. Plus negative R of the pulley times the force of the 2 kilogram mass times the sine of the angle. Why negative? Remember that force, the 2 kilogram mass, as it pulls down, it's going to cause the whole thing to rotate clockwise. Remember, that's a negative rotation. And then your force, the radius of the pull times the force of the pull times the sine of the angle, we want to add all of those to be 0. And our force, of course, is going to also cause this to rotate clockwise, which is a negative rotation. So now we simply plug these numbers in, right? We've got 0.02 meters, so that's the 2 centimeters, because our big mass, the 10 kilogram mass, is connected to the inner wheel, and that has a radius of 2 centimeters. So 0.02 meters times 10 kilograms times gravity, right? In this case, they're using 9.8 for gravity, no problem, times the sine of 90. So that gives us the torque caused by this 10 kilogram mass, minus 0.03 times 2 kilograms times 9.8. So this is the radius of the 3 centimeter. So the big wheel is connected to the 2 kilogram mass, and that has a 3 centimeter radius. So 0.03 times 2 times 9.8, right, our force, times the sine of 90 degrees. And then minus, notice that our force is being pulled from the large wheel also. So we know that the radius is 0.03, but we don't know what F is. But that times the sine of 90, that all has to equal 0. So if we do the math then, we get 1.96 Newton meters minus 0.588 Newton meters minus 0.03 meters times F equals 0. And then we want to solve for the force, and this comes out to be a force of 1.372 Newton meters equals 0.03 F. And so then when we solve for F, we get 45.7 newtons. So this is the force that we would need to apply to keep a system in equilibrium, so nothing would rotate. So let's talk about multiplying vectors, because we talked about radius and force and how we're supposed to be able to use a right-hand rule with those. There's two different ways that you could multiply multiply stuff. You can multiply things using a dot. So a dot, we get a dot product, A times B, and we put a dot between them. When we're getting A times B, we're taking two vectors and multiplying them to each other, but we're going to get a scalar quantity. This is what we do when we calculate work, right? Force times distance, and we want to use the cosine of the angle between those two vectors, because remember, when you're doing work, we need our force and our displacement to be in the same direction. So we say that dot product AB cosine theta, and that gives us a scalar product, like force times distance times the cosine of the angle between them gives me work, right? Knowing that force and displacement are both vectors, but work is a scalar product. Okay, so the examples, right? Work is one of those. Kinetic energy is another one of those. We didn't really talk about the angle between the velocities, but it is a scalar product. And then the other one is called a cross product, and this is what we talked about when we first introduced torque. A cross product, we're multiplying A times B, but we're representing it with an X instead of a dot, and we're going to use the sine of the angle between them because we want our vector to come out to be a third direction. We want our answer to come out to be as a vector. And so it's sine of that angle times n. N is the direction of that answer. All right, and so some examples, this gives us a vector product, but torque is one of these examples. Torque is R cross F, or R times F times the sine of theta, and then it's going to be at some n direction, right? Positive or negative, into the screen or out of the screen, those types of things. Another one we'll talk about a little bit later is angular momentum, which is L, and such. So that's the difference between a scalar product and a dot product. But let's talk a little bit about calculating torque in another way. Okay, so we said we could use R times F, but if we look at Newton's second law, remember net force is mass times acceleration, and we rewrite this for a rotating system, we're not going to talk about force, we're going to talk about torque. And we're not going to talk about mass, we're going to talk about inertia. And we're not going to talk about linear acceleration, we're going to talk about rotational or angular acceleration. And so we substitute these things for each other, and so instead of getting net force equals ma, we get net torque equals I times alpha. So remember that torque, which we previously said was radius times force, can also be found using I times alpha. So this is a nice thing for us because sometimes we might know radius and force, but sometimes that might be difficult for us to do, and so we treat something as a point particle, and we consider the rotational inertia of the object and its angular acceleration around something, and this just gives us another way to calculate torque. Okay, so let's take a look at how we play that out. Here's an example then. It says a 1 kilogram wheel that has a 25 centimeter radius is at rest on a fixed axis. A force of 0.45 newtons is applied tangent to the rim of the wheel for 5 seconds. So you're taking a wheel that's at rest, like our wheel, you're applying a force of 0.45 newtons tangent to the wheel, and you're going to do that for a certain amount of time, okay? And then it says the moment of inertia of the wheel is 1/2 mr squared. So moment of inertia is like saying rotational inertia. That's the I of the wheel, is 1/2 mr squared. After the 5 seconds, what is the angular velocity of the wheel, and through what angle does the wheel rotate during this 5-second period? In other words, you've applied this tangential force. After 5 seconds, what's the spin rate of this wheel, and how far did it go, through how many radians did it go to get there? Okay, so let's see if we can figure that out. So we know that we are looking for omega. We know that we start from rest. We know that the force is 0.45 newtons. The radius is 0.25 meters. They said it was a 25 centimeter radius wheel, so we converted that. We know that the mass of the wheel is 1 kilogram, and our time is 5 seconds. We also know that the inertia of the wheel can be found as 1/2 mr squared. And we know that torque is radius times force times the sine of the angle between them. Now, this z, remember, is the direction of the force. Okay, so it's either going to be positive or negative. Remember, a positive z is going to be one direction, and a negative z would be the opposite direction. So we also know that we can find torque as I times alpha. So this is a nice thing for us to do. It's kind of like saying, work is force times distance, but work is also change in kinetic energy. We can set those two equations to equal to each other, and we can solve for what we're looking for. So once again, super handy tool to have in physics. All right, so we know that omega is changing, omega is omega naught plus alpha times t, right? Alpha's changing omega over time. So let's go to work. Let's start plugging in what we're looking for. All right, so we know that torque is radius times force in a z dimension, which is also I times alpha. So we have radius and force, and we have the ability to get I, which will lead us to find alpha. So if we plug in the radius and the force, and set that equal to 1/2 mr squared times alpha, right? I is 1/2 mr squared, and then times alpha. Now we can solve for the torque on this side, and almost the torque on the other side, right? We can get alpha. So we get 0.1125 Newton meters equals 0.031 kilogram meters squared, that's I, times alpha. If we'll then divide over here, we get alpha to be 3.6 radians per second squared in a z dimension. Remember, if your force is in a certain direction, then and you started from rest, your acceleration will be in that same direction. Okay, so we have alpha, but that's not what we're looking for. We're looking for angular velocity. This is angular acceleration. And we know we started at rest, so we were looking for the final velocity at the end of 5 seconds. So we know that this will be 0 plus 3.6 radians per second squared times 5 seconds. So our final angular velocity is going to be 18 radians per second, also in that same direction, in that z dimension. So this answers the first question. Then, through what angle does the wheel rotate? We're looking for theta. Well, we've got omega, we've got time, we've got alpha, so we can use the long kinematic equation to find theta. Theta is theta naught plus omega naught t plus 1/2 alpha t squared, and simply plug the variables in, 0 plus, remember we started at 0 plus 1/2 at squared, and we get this to be about 45 radians, or approximately 7 rotations. So really, once we got past solving for alpha, this was just kind of plug and crank at that point. Okay, so let's take a look at another practice problem, and I can promise you that this example will show up in your audits. So here we have a rod, and it's got a hinge up here at the top, left corner, and it says calculate the initial angular acceleration of the rod of mass m and length L. And then it says the inertia of a rod, I, is 1/3 ml squared. And then it said calculate the initial acceleration of the end of the rod. So initial acceleration is linear acceleration. They're saying, hey, if you stood on this end and this just started to fall, what would be your linear acceleration? And then the first question says calculate the initial angular acceleration, like how fast is this going to begin to rotate once we let it go? So let's take a look at what we know. We know that objects are going to be pulled on at their center of mass. So if this is a length L, the center of mass is going to be found right here at L/2. And I know these are your favorite kind of problems because they have no numbers in them, just variables. But remember, if you were given the mass and the length, then you could come up with a number in the end. All right, so we know that this force is going to be applied at L/2, and it's going to be pivoting here on the left-hand side. That gives us a radius and a force. So we know that we're looking for the angular acceleration, alpha. It's going to start from rest, omega naught is 0. We know that that force, how would you calculate that force? Well, that force is simply mass times gravity. So it's going to be big M, because we're calling this mass M, times gravity. We know that the radius is half the length. The radius would be from the pivot point to the force. Remember, we talked about that when we were talking about defining radius for torque. So if the whole length is L, the radius is L/2, the mass is M. We know that the inertia is 1/3 ml squared. We know that torque is radius times force, which would be RF sine theta. Notice that this says it's in a negative z direction. Why is that? Because this is going to rotate clockwise. And so, so that is the radius times the force sine of 90 is 1. So this is just radius force. And we also know that torque is I times alpha. Okay, so how do you get from angular acceleration to linear acceleration? Well, in day one, when we first started talking about kinematics, we gave you that conversion. We said, hey, if you want to get from alpha, or from A to alpha, all we need is the radius. So linear acceleration is r times angular acceleration. That will help us answer that last part of that problem. Okay, so let's go ahead and get started. So the torque is r times f in a negative z direction, which is also I times alpha. That torque is going to be, the radius is L over 2. The force is mass times gravity. And that will equal the inertia, 1/3 ml squared times alpha. Now, if I do some math here and start combining some terms and rearrange to solve for alpha, I get 3L mg over 2 ml squared. So we had L over 2 times mg is L times m times g divided by 2. And then 1/3 ml squared is ml squared divided by 3, and we have to combine these two to solve for alpha. Okay, so I didn't really skip a step, I just was combining those, factoring them through. Then alpha, notice you have mass and length on both sides. So we can get rid of mass, and then we get alpha is going to be 3g divided by 2l. So that is the acceleration. Do we know what g is? Sure, g is gravity, right? That's our 9.8. So if we, once again, had numbers, we could plug those in, but this is good enough to solve for this. The linear acceleration, a, remember, is r times alpha. So the radius is L over 2. So L over 2 times 3g divided by 2l, we're going to have to factor our 2's and our l's around here. And then this will give us an acceleration of 3/4 g. Does this seem reasonable to us? Well, sure. If this was not hinged here, if we just let the whole bar drop, it would fall at g. Because it's hinged way over here and you have this long radius, the initial linear acceleration is going to be smaller than g, but pretty big still. Turns out it'll be 3/4 of gravity. Okay, this is one more problem with a pulley and two masses, and they say assume that the pulley has a mass m and radius r, and this is a disk that has an inertia of 1/2 mr squared, and they want to calculate the acceleration of this system. And so you can go through all of the steps as you follow through on the notes, and this just takes you through step by step. Okay, let's identify all the forces. Well, we have gravity pulling it down, the table holding it up, and there's a tension force to the right. Well, what about over here on the pulley? Well, there's gravity pulling it down, and it's being supported by a normal force off that little shaft there, and then there's tension force this way, and there's a tension force going down. Well, what about on mass 1? Well, you have gravity pulling it down and a tension force pulling it up. So we've identified all of these forces. These forces that are up and down on this block cancel, and so we want to look at the net force on this block. The net force on the pulley is going to be the tension here minus the Ft1 here, and the net force on this block will be gravity minus the tension force here. So if we're looking for the acceleration of the system, we need the net force on the system and the total mass of the system. So force, remember, is mass times gravity. Net force on block 1 will be the force due to gravity minus the tension force. So that's M1A is M1G plus negative Ft1. And so if you solve for Ft1, you get M times G minus A. And then the net force on block 2 is simply the tension on force 2. And so that's M2A equals F2T. And then the net torque is going to be torque 1 plus torque 2. The net torque on the pulley, right? We've got a torque this way and a torque this way. So torque is I times alpha, which is radius times force plus radius times force. We know I is 1/2 mr squared. And so we do also know that these forces and the radius are at 90 degrees to each other, and that the torque from this one is going to cause it to rotate in this direction, and the torque from this one's going to cause it to rotate in that direction. And so then we can set I and alpha, torque, and solve for acceleration. I got this in the way. The acceleration is radius times alpha, or alpha is a divided by r. And so we have several equations, and then we have 4 unknowns, because we don't know the acceleration, we don't know the angular acceleration, we know the radii and the masses, but we don't know the tension forces. Lots of things we don't know. So when you do that, you set several equations equal to each other, right? I alpha equals the sum of the torques, and then solve for, continue this step by step. You guys can follow through this. I won't give you a problem that's that difficult, but I want you to know that you have the ability to do that. I will give you a problem very much like the bar and falling down and trying to solve for the acceleration of that. But once again, what's your process? You're setting torque equal to torque, R cross F equal to I times alpha. And if it's not I of a solid point particle or a ring, you'll be given what that R value is. I mean, that inertial value is.